Okay, this is the third video then. So we're doing questions 21 to 30 on November 2016. So we just started the rate section. So 21, which statement describes the characteristics of a transition state relative to the potential energy of the reactants and products? Remember, if you have like an energy profile diagram, and let's say it was for an exothermic reaction, just as an example, then what we've got is the activation energy is up to the top of the hill and then down to the products. So here's our reactants, here's our products, and we've got our activation energy up here. And this is basically at the top of the activation energy, this is where we find our transition state. Sometimes kind of written like that, TS is transition state. So transition state is a very unstable species which could go either way. It could go back to the reactants or it could go on to the products. So we're looking for an unstable species, and notice it's a higher energy than the reactants or the products. So unstable species, yes. Lower potential energy, no. It's a higher energy. Unstable species, yes, with higher potential energy. Yeah, that's looking good. Stable species, no. Stable species, no. So we're looking for B. Okay. You can't isolate transition states. They're very, very unstable. They're not intermediates like a carbocation in the SN1, for example. So remember in SN2 you get the transition state more where you get a nucleophile coming in as the leaving group departs, and this is a very unstable species, whereas if it had been proceeding via an SN1 where you'd have the carbocation, well, that would actually be an intermediate, which generally not isolable, a carbocation, but I seem to recall you could get ones where I think there were sort of some like 3 phenyl groups on it, which might have been almost stable enough that someone actually isolated it. Off the sheet there. So yeah, that's what I was talking about. Sorry, I wasn't sure it was off camera. So yeah, here we've got an example of a transition state. Very high energy, very unstable. You wouldn't be able to isolate that. Whereas here we've got more of an intermediate. This would be what you'd get in SN2. So we get in SN1. Anyway, it's just a little bit of extension of the question. 22, more rates. So decomposition of hydrogen peroxide in aqueous solution proceeds as follows. 2 hydrogen peroxides give a couple of waters oxygen. Rate expression of the reaction was found to be rate equals K times concentration H2O2. So there's a 1 there, we'd have to imagine. So it's first order with respect to the hydrogen peroxide. So which graph is consistent with the given rate expression? Well, here we've got rate versus concentration. Now, if it was first order, it would be directly proportional. So this looks more like the rate concentration graph if it had been second order, because if it was second order with respect to hydrogen peroxide, we would get a curve. If we wanted to make that directly proportional, what we could do is plot we could plot the square of the concentration. So if we plotted the square of the concentration against rate for a second order, we would get a straight line directly proportional. But this is only not the case, because yeah, if it was first order, we'd see basically we'd be looking for that arrangement, so it's not this one. But when we see this one, we automatically sort of think, oh, that's zero order, so it's not this one, because again, this is where concentration has no effect on the rate, so this would be zero order, so it's not this one. Again, this one, when we see this is zero order. Basically, when you get sort of a straight line like that, this is zero order as well. So as the concentration of the hydrogen peroxide it decreases at a kind of a uniform rate against time. So pinning all hopes on this one. So we've got concentration against time rather than concentration rate one. So that's about right for first order. Second order is tricky to spot. I think the second order can maybe sometimes be a bit steeper, but it's very tricky to tell. The way you would be able to tell from the graph is if you measured there was a constant half-life. So let's say sort of the reaction decreased by sort of half its concentration after 10 seconds, it would halve its concentration again after a further 10 seconds and so on. But this is really the only possibility left now, so we don't have to worry about whether it's first or second order. I'm going with D as being the right answer, I say. Number 23, the rate constant K is commonly described by the Arrhenius equation, K equals A times the exponential minus A over RT, which the following statements are correct. So we don't often deal with the Arrhenius really in this format. Normally when we use the Arrhenius, of course, we have it in its logarithmic form, which is where those of you who've done IEAs with activation energies, I would be more familiar with that, where we can then use it to find the activation energy, the graph. So looking through some of these statements then, so a greater EA value results in a smaller K value. Now, sometimes you sort of think, okay, well, I could follow it from the equation. So like, okay, what would happen if EA got bigger? But then I'm not really that familiar with exponential, to be honest. I normally let the calculator do all the heavy lifting for me there. So if EA got bigger, well, I've got no idea what that would then sort of have as an impact once you've done the exponential of it. My maths knowledge isn't strong enough, I'm afraid. So I'm going to have to try and sort of rationalise it through a bit more instead, rather than use the equation personally. So let's try and sort of have a bit of a think about it. So remember that rate equals K times the concentration of whatever reactants there are. And the bigger K is, the faster the rate is. So if we've got a reaction with a large activation energy, that's going to be a very slow reaction. A very slow reaction is going to have a small value of K, because you've got the concentration times K. The smaller K is, the lower the rate is. So I'm kind of rationalising this one makes sense in that a big activation energy is going to make the reaction very slow, and if the reaction is very slow, then it makes sense that K is very small. So I agree with that one. Reactions of less complex molecules usually have a greater value of A. Again, I'm not really that familiar with the A itself. We normally don't really focus in that much on it. I'm just going to come back to that one. The slope or gradient of natural log of K versus 1 over T equals EA. Well, again, when we take the natural logarithm of this bit, natural log of K equals natural log of A plus minus EA over RT. And of course, when we substitute in, that's Y equals mx plus C. So this is C, and then EA over R. So yeah, let's define these terms. So Y is natural log of K. M, or X rather, is 1 over T. C is the natural log of A. So M is this kind of bit here then. So M is minus EA over R. So your gradient is not actually EA itself, it's the negative EA over R. And that's why when you do this sort of form, what you have to do is find the gradient, and then you've got to basically change the sign. The reason why this is, you get, if you've got like a sort of a graph, you're down in this quadrant when you plot 1 over T against, natural log of K down here, 1 over T along your x-axis, you're down in this quadrant, and of course that's a negative gradient. Activation energy though is always endothermic, it's a positive value. So the reason we've got the minus is it then cancels out the negative gradient. So what we'd have to do is find the gradient, make it positive, and then multiply by the gas constant R, which I think is 8.31 off the top of my head. So yeah, so I disagree with that. It's actually equal to minus EA over R. So I don't agree with that one. So 3 is not right. I'm still not sure about 2, but 1 is okay. So maybe this will help out, because sometimes a possibility isn't there. So maybe I don't have to actually worry about 2. So A, 1 and 2 only. So I do have to worry about that. So because it could be this. We've got 1 and 3 only. Well, I don't know. It's definitely not that. 2 and 3 only. I know it's definitely not that. Actually, I've kind of done it by process of elimination, haven't I? Sort of, I have made myself, because I know it's not 3, and 3 features in all of them. So it's got to be A. So thinking a bit more about this now. So reactions of less complex molecules usually have a greater value of A. Well, I know that A is like to do with the collision frequency, or the kind of collision factor. And basically, it's the more these molecules collide, and with the correct orientation, the more reaction you're going to get. Now, I can see that if you had a more complex molecule, that would make it harder for the molecules to collide. Because let's say we had, again, sort of thinking like an SN2 reaction. Well, if I had a carbon chlorine, remember the nucleophile has to come in from the back, the opposite side to the chlorine. But if I then got a molecule which has got a long carbon chain, let's say, hanging off the back of it, Well, that could be constantly getting in the way all the time, just kind of like, so like all different orientations where it's kind of blocking the nucleophile from coming in and attacking. So I can actually see this making sense in that less complex molecules. So let's say, for example, if we compared it with this one, where we just had hydrogens coming out the back. Well, it's nice and easy for the nucleophile to get in there, because these hydrogens can't really get in the way at all. They're all sort of locked in space. There's no other kind of what we call degrees of freedom of having like a long chain, where that chain could then just be sort of orientating itself around and kind of blocking the backside of the molecule, even if it's just, you know, not permanently bonded there. It just happens to be occupying that region of space. So I can actually see quite a bit of sense to that, but process of elimination has helped me anyway. So I'm going with A. 24, it's like we're into equilibrium now then. So what happens when the temperature of the following equilibrium system is increased? Now I'm awful at sort of, and that's why I remind myself every time now about, right, okay, so temperature, remember, does affect the equilibrium constant. It's the only thing that does. So temperature is changing, so the equilibrium constant will change. Doesn't look like that's actually part of the question, but it's just I'm always on guard for that because I always forget it. Because remember, sometimes if I change the pressure and then you sort of think, oh right, so you're going to make more products or your equilibrium constant is going to get bigger. No, it's only temperature that does that. So let's look at the reaction. Here's the reaction, and it's got a negative enthalpy change in the forward sense, so it must be exothermic going forwards and endothermic going backwards. If we increase the temperature, that's going to favour the reverse endothermic reaction, so it's going to shift to the left, because again Le Chatelier principle says that it tries to do the opposite of what you've just done. So if we increase the temperature, it'll shift to the left, and the reason being that the reverse reaction is the endothermic one, because the fact it's minus 91 means it's exo going forwards. And then this is where you have to think of it a bit separately then. You might sort of think, oh well, if it shifts to the left, it must be that it speeds up the reverse reaction and slows down the forward one. No, that's not true. Think of it as two different people really. You've got Mr. Equilibrium and Mr. Rates. And it's whatever the case is. For Mr. Rates, if you increase the temperature, you increase the rate. It doesn't matter what reaction it is. So the rate of the reaction is going to increase. Both of them will increase. So it's going to be here. Now remember, at equilibrium, both reactions are going at the same rate. So that's why we don't observe any change in concentrations. If we increase the temperature, we increase the rate of both reactions. So let's say sort of this is the rate of both reactions at the start. So forward, backwards. If we increase the temperature, they both get faster, but one gets faster compared to the other. So this would be the rate of the forward one, this would be the rate of the backward one. And that's why the equilibrium then starts shifting, because the forward reaction is occurring, the backward reaction is occurring at a faster rate than the reverse one. So once again, we then get an equilibrium where the rates are once again equal, but we will have a new equilibrium mixture. So this reaction is going to have to get a bit quicker, this reaction is going to have to get a bit slower until they're once again equal, but we'll end up with a new equilibrium mixture. But yeah, bottom line, if you increase the temperature, you increase the rate of both reactions. It's just not equally, and that's why there's a shift in favour of the endothermic reaction. 25, again, we've got equilibrium. A mixture of 0.4 moles of carbon monoxide, 0.4 moles of hydrogen was placed in a 1 decimeter cube vessel. They're giving us a nice easy number there, because, of course, if it's an equilibrium, we need concentrations unless you've got the same number of moles on both sides. We don't. We've got 3 molecules on the left and only 1 molecule on the right, so we need concentrations. Number of moles is not good enough. Because they've given us 1 decimeter cubed, effectively the number of moles is still the concentration, because it would just be the concentration would be 0.4 divided by 1, 0.4 divided by 1 there. At equilibrium, the mixture contained 0.25 moles of carbon monoxide. So how many moles of hydrogen and methanol were present at equilibrium? Well, there's not much space there, but we want to kind of create an ice table. So carbon monoxide plus 2 hydrogens gives our methanol. Then remember, what we're looking for is ice is initial change and then equilibrium. So at the start, we've got 0.4 moles of carbon monoxide, and we've got 0.4 moles of hydrogen, and we've got no moles of methanol. At the end of the reaction, at equilibrium, we've got 0.25 moles of carbon monoxide. What's the change? Well, it's gone down from 0.4 to 0.25, so that difference is minus 0.15. So it's gone down by 0.15. You might think the hydrogen is going to go down by 0.15 as well then, as the other reactant, but they react in a 2-to-1 ratio. So if 0.15 moles of this stuff has reacted, then double that amount, 0.3 moles of hydrogen will have reacted. So 0.3 moles of hydrogen will have reacted because it's a 2-to-1 ratio. So I know it looks confusing because you think, well, you start off with the same number of moles, yeah, but they don't react in a 1-to-1 fashion. Fact is, at the end of it, you know, sort of the carbon monoxide is in excess. There's not enough hydrogen, because for the hydrogen to react completely, we would have needed 0.8 moles carbon monoxide. But then the reaction is reversible anyway. So it's going to go from 0.4 down to 0.3. I will have 0.1 moles. Now, carbon monoxide and methanol are 1-to-1, so if 0.15 moles of carbon monoxide has reacted, it has created 0.15 moles. And again, don't go thinking, oh, adding these together, because it's just like playing the mole ratios basically. 0.3 moles of this would be enough to make 0.15 moles. That's gone up, 0.15 moles. So we're looking, okay, the equilibrium amount of hydrogen is 0.1, so that's this one. The equilibrium amount of methanol is 0.15, so that's this one. So that's it. 26, we're on to acids and bases then. So we've got which species behave as Bronsted-Lowry bases in the following reaction. So again, always be careful to read the question, because if you sort of second guess it, a common question is, say, which is the acid-base conjugate pair? So you might then be sort of thinking, oh, actually it's those two, but they're not after the acid-base conjugate pair. They want the two bases, because there'll be a base on the left and a base on the right. So we're looking for the bases in each acid-base conjugate pair. So remember, the acid would be the one with more protons. So if we look, H2SO4 and HSO4 minus are an acid-base conjugate pair. H2SO4 has got more hydrogen, so it must be the acid, and HSO4 must be the base. Looking at the next bit then, we've got HNO3 and its conjugate partner is H2NO3 plus. Which one's got more protons? That would be the acid. Well, it's this one. So this would be the acid and this will be the base. Now I know you might sort of think, well, that's crazy. Nitric acid is an acid. It can't be a base. Well, here it is, because sulfuric acid is a stronger acid and is able to force a proton onto nitric acid. That's why this stuff is actually very unstable then, and then it decomposes to form water and the nitronium ion, which of course then would react with benzene in a nitration reaction. Okay. So which of the two bases then? So we've got base there, so we're looking for A, looks like the right one. Yep. 27. So more on acids and bases. So what occurs when solid sodium hydrogen carbonate reacts with aqueous sulfuric acid? Bubbles of sulfur dioxide form. Well, no, that's nonsense. Because I say that's just baking powder. You know, baking powder giving off toxic fumes of sulfur dioxide. Bubbles of both hydrogen and carbon dioxide form. No, this is nonsense. Because again, you might be sort of thinking, oh, well, wait a minute, there's hydrogen in there. But if that was sodium carbonate, it would still just give you carbon dioxide. So basically, sodium hydrogen carbonate is this stuff, NaHCO3. And then that's going to react with sulfuric acid, which is H2SO4. We'll get sodium sulfate, which is Na2SO4, plus water, because it's a base at the end of the day. This stuff, it's a base and it's a neutralization, but it's also a carbonate, so we get CO2 produced. To balance it up, because I've got two sodiums here, obviously I need two of these sodium hydrogen carbonates, and then that's going to be enough to give me 2 carbon dioxides and 2 waters. Yeah. So bubbles of hydrogen form. Well, no, it's not a metal. Remember, you only get hydrogen gas when it's a metal reacting with acid, like a MASH reaction. So we're not going to get hydrogen. It's bubbles of carbon dioxide form. That's the reaction. Which mixture is a buffer solution? Okay, so looking at these ones then. So, well, ammonia will react with HCl to make ammonium chloride. So that would give you ammonia and NH4Cl, which is effectively then you've got NH4 plus. So I'm liking these two already because we could get buffer solutions, but you sort of think, right, we've got a weak base and a strong acid, and then that's going to then kind of give rise to the ammonium ion. So these two look very similar. Looking at these two, well, here we've got a strong base reacting with a strong acid. So you're not going to get buffer systems from those. Because what you're going to get here is basically NaOH plus HCl reacting to make just sodium chloride. Well, sodium chloride can't act as an acid or a base, and you're just going to get water produced. Because the idea of a buffer system is, remember that if you've got a weak base, then its conjugate acid is not a bad acid. Whereas what we've got in the case here is we've got a strong base and its conjugate acid, which is water, is not a good acid. And here we've got a strong acid, and we're sort of saying, right, its conjugate base, which again would be water here, is not a good base. So we're not going to get a buffer system from these ones, where you've got a strong acid and a strong base. Because what we need is at least a weak base or a weak acid, because then its conjugate partner will be quite complementary kind of thing. It won't be a half bad acid or base itself. So it's going to be one of these two. I've eliminated them. So now looking at these, well, what we've got going on here, we've got 25 centimeters cubed of 0.1 molar. Now remember, these are going to react in a 1-to-1 fashion. Ammonia is going to react with HCl to make ammonium chloride as is. So I've got 25 centimeters cubed of 0.1 mole per decimeter cubed ammonia, and I'm reacting it with a larger volume of the same concentration. So here we can see the HCl is in excess. Now the idea of a buffer system is that I have a healthy reservoir of both things. I need quite a lot of ammonia and I need quite a lot of ammonium. So that's the idea of the buffer system. It doesn't have to be 1-to-1, it depends on what pH I want, but I need a reasonable amount of both present, the base and its conjugate acid. In this reaction, I'm not going to have any base left because the hydrochloric acid's in excess, because we can see they're the same concentration, but I've got double the volume of the HCl. They react 1-to-1. Whereas in this one, I've got double the volume of the ammonia, and I've got half the volume of the hydrochloric acid. So I'm going to react half of the ammonia to give me ammonium, NH4+. So this is going to give me a 1-to-1 mixture of ammonia and NH4+, and that's my buffer reservoir then. So B is going to be the right answer. 29, which salt solution has the highest pH? Well, if anything, this is a source of protons, so that's actually going to be a little acidic, if anything. Nitrates and sulfates, they're just pretty much salts. They don't really affect the pH very much. Sometimes you can get sort of a bit of Lewis acidity going on with the metal ion, but not particularly thinking about those. So hopefully this one looks pretty good. Sodium carbonate. Well, carbonate, as we saw up here, is quite a good base, and if it dissolves in water, and all group 1 salts are soluble in water, then it will form an alkaline solution. And the way you can form an alkaline solution is your carbonate ion can react with water reversibly to create the hydrogen carbonate ion. It can basically steal a proton off the water, and you've got your hydroxide ions, which is what's going to increase the pH. So with hydroxide ions being created in this one, because it does dissolve, it's soluble because it's a sodium salt, the carbonate will react reversibly with some of the water and create hydroxide, so I'm going to go with C. Okay, so that's going to increase the pH. Number 30, so we're on to redox. So we've got 2 permanganate ions, hydrogen ions as acid, nitrite ions, and then they're creating manganese 2+ nitrate and water. So we've got to identify reducing oxidizing agent and what's going on with the oxidation numbers. Now where you'll save yourself a bit of time, remember, is permanganate is a very strong oxidizing agent. So if you remember that, you've already made your lives a bit easier here, in that it's probably acting as an oxidizing agent because it's a very strong one. Let's back that up with the oxidation numbers though. So let's see what's going on with the oxidation numbers. We're just going to focus, so it wants the nitrogen as well, so let's go down a bit more, let's just do them all. So oxygen of course is -2, as it usually is. The only exception would be oxygen itself, O2, where it would be 0, and hydrogen peroxide was -1. So oxygen is usually a safe bet to say that it's -2. The whole ion has a minus charge, and there are 4 of the oxides, so they would have taken it down to -8. 4 times -2 would be -8. What's brought it back up to -1? Well, that 1 manganese must be in a +7 oxidation state then. The hydrogen ions here would have to, well, maybe the charge on the ion would be +1, not that we need to worry about that. Oxide again, or the oxygen is -2. That comes to, there's 2 of them, and it's 1 minus overall. So that would be 4 minus. What's bringing it back up to that? The nitrogen must be in a +3 oxidation state. Nothing to worry about the 5 in front, you're just looking at the NO2 minus, that's all you're looking at. Here again, it matches the charge on the ion. And then we've got the nitrate -2. Now it's -6 up to -1, so your nitrogen must be +5. Again, hydrogen +1, oxygen -2. So it is a redox reaction because there's a change in oxidation state. So the manganese is going from +7 to +2. So your manganate oxidation number decreases. And if oxidation number decreases, then it is being reduced. But remember, if it's being reduced, that means acts as the oxidizing agent. Because if it's being reduced and gaining electrons, it's taking them from something else, so it acts as your oxidizing agent. Let's put that in as well. It goes from +7 to +2. And then again, you don't need to put all this level of detail, okay, because you're using up valuable time in the exam, of course. I'm just kind of like embellishing a little bit to try to sort of help explain some of the chemistry, what's going on here, touch upon a few other bits and bobs. But keep an eye on the time. You don't have to write all these notes. The examiner's not going to sort of see them anyway. And then your nitrite then, so your NO2 minus, well, that oxidation number increases. Goes from +3 to +5. So it's oxidized, which means that it's actually the reducing agent. So it's reducing the other one. So permanganate is the reducing agent. Well, that's wrong. It's the oxidizing agent. Permanganate is the oxidizing agent. Yes, that's right. Let's check here. When the oxidation of manganese increases, well, again, that was wrong. It goes from +7 down to +2. Permanganate is the oxidizing agent, and the oxidation number of manganese decreases. That's looking good, +7 to +2, so that's looking fine. Let's just eliminate the other 2 possibilities. Nitrite is the reducing agent. Well, yes, it is. And the oxidation number of nitrogen decreases. Well, it doesn't. It goes from +3 to +5, so that bit's wrong. And nitrite is the oxidizing agent. No, it's not. It's the reducing agent. It's oxidized itself. And the oxidation number of nitrogen increases. Well, yes, that is true, but the first part's wrong. So the only bit where they're both correct is for B. Okay? And that's the third video done.